All right, hello and welcome to our discussion about complex numbers. Got a lot of stuff to cover today, as well as some review on radicals. So we want to define and use the imaginary unit. The imaginary unit is identified as I. We're going to talk about simplest form of radicals. We're going to add, subtract, and multiply radicals using I. And we're going to add and subtract and multiply complex numbers. Division we'll save for pre-calculus, and then we want to find complex solutions and zeros. All right, so let's get started. So I'm going to have you work along with me. I want you to factor this quadratic. So you can pause the video. And when you're ready, come back. Okay, so we factored it into y is equal to x minus 3 times x minus 1. Now, can you graph this quadratic? Where does it face? What are the x-intercepts? What's the y-intercept? So you can quickly sketch it. Please pause here. All right, so you should get something that looks like this. I have a quadratic that opens up. The two x-intercepts, 3, 0, and 1, 0. All right, can you tell me where the graph crosses the x-axis? You can pause here. Graph crosses the x-axis at 3, 0, and 1, 0, so those are the x-intercepts. What are the roots, zeros, and solutions? You can pause here again. All right, we have x is equal to 3 and 1. And that's it. So we've taken a quadratic, we've factored it, we've graphed it, we've found the x-intercepts, we've found the solutions to the function where y is equal to 0. All right, can you factor this quadratic? And then can you graph it? Find out where the roots, zeros, or solutions are and where it crosses the x-axis. So take a moment. You can pause here, please. All right, so you can't factor this quadratic, at least not with integers. We can graph the quadratic. If you were to do this on Desmos, you would see the quadratic looks something like this. If you wanted to find the roots, zeros, or solutions, you need to use a quadratic formula, but you're going to end up with the square root of -8. So the question is, what is really the roots, zeros, or solutions? And how do we represent the square root of -8? And then where does the graph cross the x-axis? And the answer is it doesn't. All right, so if we consider roots, zeros, and solutions where the graph crosses the x-axis, and this parabola never crosses, then we're left with the question, how do we represent a root, zero, or solution? And the answer is we're going to represent it as a complex number. All right, so can you give me the roots of this quadratic? And so we're going to take that value, x squared plus 2x plus 3. And we're going to use a quadratic formula. This is how I got these values. So you can take a look at the work and pause this here. But I end up with -1 plus or minus I root 2. If you do the work and the simplifying, you can see that this is the value that you end up with. So these are the roots of the quadratic, some complex number. So let's talk about what that is. All right, so then we'll step back a second and we'll talk about parabolas. So the possible forms for parabolas are A, I have two solutions where the parabola crosses the x-axis in two locations. And again, these are for parabolas that open up, down. We also have parabolas that open right and left, which you'll talk about in pre-calculus. You have parabolas that touch the x-axis in one location. So there's one solution, and that's going to be at the vertex. And then you have parabolas that never cross the x-axis. So in red, there are no real solutions. There are imaginary solutions, but not real solutions. So we need to represent these solutions in an imaginary way. And so we need some type of lettering or understanding of what that means. All right, so let's talk about radicals. We're going to talk about imaginary numbers in the context of radicals. So an imaginary number is defined as the square root of -1. And the symbol for an imaginary number is I. And it would be this lowercase scripted I is typically how it's written. But you can also write it as lowercase I with a dot. I is going to help us to define the roots of quadratics in an imaginary plane. And I has practical uses in the study of physics. All right. So let's move on. So one thing I want you to take away with is I is equal to the square root of negative 1. Square root of negative 1, or I, is an imaginary number. And it does, in fact, have some practical applications. All right, so simplest form of radicals and I. All right, a simplest form of a radical is a radical which has no perfect nth roots or square roots in the radicand. So if I take a look at its factors of the radicand, square root of 8, I have a factor that's a perfect square root. All right, and that's 4. I take the square root of this, I end up with an integer value of 2. So the properties of radicals say I can separate the square root of any integer into the square root of the two factors. In this case, 4 and 2. So the square root of 8 is, break this up into the square root of 4, its factors times the square root of 2. 4 is a perfect square. I have a perfect nth root of 2, so I end up with 2 root 2. Okay, so simplest form, a radical is in simplest form when it has no perfect squares in the radicand. You've simplified those perfect squares. In this case, square root of 4 is 2. Its denominator has been rationalized, meaning there are no radicals in the denominator. Right? We're going to take care of this in pre-calculus. So I'm not going to give you any examples where this is an issue. And then finally, like terms are combined. We're going to talk about like terms. So what we're going to work on here is making sure in the radical, there are no perfect squares as factors. In the radicand, and this is the radicand value, and like terms are combined. Like term has the same radicand value, 2 and 2. And I can add these two together. 3 root 2 plus 4 root 2 is equal to 7 root 2. And I think I mentioned before that you need to go through the lesson on radicals before getting to this point. So if you haven't already, please go back and listen to that. Okay, so simplest form, a radical is in simplest form when also the radicand is positive. So the square root of negative 7 is not in simplest form. We want to write the square root of negative 7 as the square root of negative 1 times the square root of 7, which is the same as I root 7. So we said that there are no perfect squares as factors in the radicand. We said that like terms are combined, and then we said that this radicand value is not negative. So we're going to use a value of I and what we know about separating out factors from a radicand. I can rewrite this as the square root of negative 1 times the square root of 7. So then I can then convert the square root of negative 1 to I. Ultimately, you'll see this intuitively as I root 7. And you won't need to go through this step here. All right, so simplifying radicals with a negative radicand value. One is we want to separate the radical into its factors using the square root of negative 1 as a factor. And then any perfect squares as factor. We have 4 as a perfect square, and then non-perfect squares. Right, so we have the square root of negative 1, perfect square, non-perfect square. And we end up with I times 2 times root 3. Now it doesn't matter what order I and 2 come in, but my preference is that you write the number, then I, and then the radical in order. All right. So once again, I have the square root of negative 12. I'm going to take the square root of negative 1 as a factor because this is equal to I. And remember, simplifying this radicand value requires that it is a positive value. Then I'm going to take out any factors that are perfect squares. I'm going to simplify those. And then I'm going to rewrite with the number I and then the radical in that order. Okay, so let's simplify these radicals. I want you to see what you can do. I'm going to pause here, or you can pause, please. I am going to give you the answers, but let's see what you can do. Okay, the first one, square root of negative 1, I have a perfect square of 49 times 2, square root of 2 gives me 7I root 2. Second, square root of negative 1, I have a perfect square of 64. Square root of 64 is 8, and then root 2, 8I root 2. Last one, I have square root of negative 1 times a perfect square of 4 times square root of 6 leaves me with 2I root 6. All right, that's how it works. That brings us to our first classwork problem, 3.2.1. I want you to simplify these radicals. So you're going to pause here and write these down. So take a moment, and then I am going to move on to our third topic. We're going to add, subtract, and multiply radicals with I. All right, so the adding and subtracting part, and we need to talk about like terms. So like terms for radicals, I have the same index, it's right here, and the same base. All right, the index that you've seen so far for radicals has been 2. It's the square root. But I can also take the cubed root of some value. The cubed root of 8 is 2. 2 times 2 times 2 is 8. The cubed root of 8 is 2. We can take the fourth root of 16. That's also 2. 2 times 2 times 2 times 2, 4 times 2 times 2 is 4. Another 2 is 8. And then finally 16. I can take the fourth root, right? And so that root value is listed in this pocket here in the radical sign. We're just dealing with roots or indexes of 2. Index of 2 is not stated when it's a square root. All right, so it needs the same base and the same index. And the index other than 2 is something you'll work with in pre-calculus. But I want to go through this with you. These are like terms. I have the same base and same index, so I can add these together. Multiplying is a different story. So 2 times the cubed root of 7. That's okay. If I have the cubed root of 7 plus the square root of 7, there's nothing that I can do because these are not like terms. You cannot add terms that are not like together or subtract. All right. You have to keep them separate. Separate terms. All right, so now let's consider just what we want to consider for Algebra 2. Same base, we're dealing with square roots only. All right, so the requirement is we have the same base if we want to add. If we want to multiply, again, or divide, it's a different story. Square root of 7 plus the square root of 7 is, I have 2 square roots of 7. 2 times the square root of 7. The square root of 3 plus the square root of 7, they're both not like terms. So I'm not going to simplify that any further. It ends up being the square root of 3 plus the square root of 7. All right, so real and imaginary. Real and imaginary numbers are not like terms, so these terms cannot be combined. Of course, I can add 2 and 2. That's equal to 4. I can add 2i and 3i because those are two imaginary numbers that are like terms. 2i plus 3i gives me 5i. But 2i plus 3 I cannot simplify because they're not like terms. Okay. If the coefficient is an imaginary number, so 2i, then I can also add that to a coefficient that's an imaginary number, right? So I can add numbers that are imaginary only, or I can add numbers that are real only, but I can't add imaginary numbers to real numbers and simplify them. I can in terms of some value, but not in terms of simplification. All right, so 2i root 7 plus I root 7 is 3i root 7. 2i root 7 plus 2 root 7 is 2i root 7 plus 2 root 7. Right? I can't simplify this any further. And then I have no I values. 2 root 7 plus 3 root 7 is 5 root 7. You see, so if I'm adding imaginary numbers together, I can add those together. If I'm adding just real numbers together, I can add real numbers together, but I can't add and simplify an imaginary number to a real number. All right, so this is classwork here. Why don't you take a look at this, see if you can do this. I'm going to pause and stop, and then we're going to rejoin. So let's pause here for you. Let's see if you can do this, and then we'll come back with the answer. So please pause.